So let's take a look at the idea of the geometric optics first point. Okay, so what we're trying to understand is how to explain what we see technically. Okay, so that's what the idea of the geometric optics means, which means I think you guys familiar with the electromagnetic spectrum at this point. Because at the end of the 290 class, we talk about Maxwell's law, Maxwell's theory. So in Maxwell's theory, we talk about four Maxwell's equations, how those equations correlate, integral version, differential version, things like that. So that's a very, very foundation level of electromagnetism. That where the electromagnetism is start. In real electromagnetism is start. Okay. So if you think that we can say we know electromagnetism after completing PH by 290 class, you have to think twice. So in physics, the real E and M class is starting from the Maxwell's equation and above. So anything below is like considered as a very general knowledge everybody should know. So because of that, you have to be careful when you're talking about I know E and M theory or something. Be very careful. Okay. So technically, that class doesn't count towards that in terms of physics perspective. Okay. So anyway, so in that class, we talk about Maxwell's equations. So the one of the important discovery or the result which came out from the Maxwell's equation is the understanding of electromagnetic oscillations. So that never been done before, theoretically or even experimentally. People had some idea about what is visible light, the radiation. People had some idea because experimentally those things were investigated. However, there wasn't any theoretical model or theoretical explanation what the light is and then so on. So that's why the EM theory is so uniquely very important. So in his theory, he calculated the one particular constant we nowadays call is the light speed, which is about like 2.99 times 10 to the 8 meter per second. Now, when the Maxwell calculated that out of his theory, this is actually result from the epsilon 0 and the mu 0, right? 1 over epsilon 0, mu 0 is square root should be equal to that constant. That's it. You know what is the epsilon 0, what is the mu 0. One is electric constant, other one is the magnetic constant at free space, or we generally call the air. And if you put those numbers, you know those numbers, then you will get a constant. So that constant is actually this constant right here. So then he predicted that if there is oscillating electric field and oscillating magnetic field, those oscillation can generate a single quantity and then can move in one single direction. So which means if I have electric field oscillating on XY plane, and then if I put the magnetic field maybe XZ plane, so these two can actually create a single quantity and then move in one particular direction. So the E field oscillation in XY plane and then the B field oscillation on XZ plane, and the resultant the propagation direction is actually X direction. So that quantity is actually he called electromagnetic waves. And then the speed of that electromagnetic waves in air, or air means generally we call the free space, okay? Free space or air, it should be about this number, 2.99 10 to the 8. And it took about like 60 years after his prediction to experimentally calculate that number by using the light speed. So that's the Michelson experiment. So which is a very famous experiment again. So however, the idea from that is actually generating what we generally nowadays call the electromagnetic spectrum, because idea from there is actually generate all the energies in the universe can be put it into one single place, which we nowadays call the visible energy or measurable energy, because we know now dark energy exists, but we don't know how to detect that or how to measure it or anything yet. Okay, nobody don't know in our world. Maybe another world somebody know. So if we get rid of dark energy and dark matter, the everything in the visible, observable universe, what we call about 14 billion years back in time, we can observe nowadays, right? Roughly. So if we consider that visible universe, in the visible universe, everything in observable energy, we can put it into the EM spectrum, right? So which means the gamma rays, X-rays, UVs, and then we have a small region where we call the visible light. Very, very small region. And then infrared, then you have microwaves, TV waves, radio waves, and then so on. This side is very low energy side. This side is very high energy side. So which mean these radiations are not good for human, generally for living organisms, because our cells and everything can damage. That's why all of those are considered as not good. And these sides are low energy, so nothing much to worry, because around us there's millions of billions of TV waves, microwaves, whatever the other mobile waves, everything is there, right? So nothing much to worry. That's not going to harm anybody. Now, what we really interested in this particular chapter, geometric optic, is actually this part, visible spectrum. So that is the only part we can directly see, human can directly see. There's animals maybe sensitive to the other regions like UV and IR particularly, but the human's eye is sensitive only to the visible, right? If you expand that part little bit, zoom in, then it can go like maybe 700, 400 nanometers to about like 700 nanometers in wavelength. That region means, now you guys know what's a wavelength and frequency, those things, okay? So which mean this lower wavelength region mean the higher frequency region. Higher frequency region very close to the very dark blue to purple. So that means this side is blue. Lower frequency or the higher wavelength region is the low energy region, that is a red side, okay? So in between we have other colors, green, yellow, things like that. So that we generally call the rainbow colors, right? So now what we're really interested is to understand this particular part only in the spectrum. So that's why all the connection is actually so important. And not only that, this electromagnetic spectrum connect what we generally call the radiation energy, right, nowadays. That radiation energy is actually related to the energy quantization in quantum mechanics, very basic level. So that first hypothesized by the Max Planck. So he explained that any quantized energy should be quantized into some sort of quantity. That's a quantization means what we generally call nowadays energy packet. So that should be based on the frequency of the wave and only the Planck constant. So that guy is about like very small number, 6.56 times 10 to the negative 34 joule per second. So extremely small quantity, okay? So which mean any of the energy, what the CM waves does carries the energy. When it carries the energy, those energy should be carries as a energy packet in quantum level. Now that is actually what optics really means. So which mean we have to go towards the quantum optics to really better understand what the optics really means. That is not our purpose in this chapter or in this class either in general. So what is our purpose is actually to understand, because we know this part is visible, we can see them, which means you can see what is around you, which means your eye is actually creating some sort of image of whatever you've seen. Technically, that's what the visibility means, right? So you've seen something look like out there, but actually what you're really observing is an illusion which is actually generating on your brain. So technically what you actually doing as an observation. So which means we would like to understand that physical process, not anything else. Okay. So the conservation of energy or anything we don't need. So we're not going to be talking about quantum physics at all. Okay, so that's a few semester long course, can be done only at higher level physics majors, or maybe third year, fourth year, you can take the very basic quantum optics class. After quantum mechanics done, not the quantum mechanics we do in this class. Don't tell anybody we even doing quantum mechanics in this class because we're going to be going through very, very basic knowledge. Okay. So when you become a physics major, then you have to take two quantum mechanics classes, probably third year, fourth year level. I took in second year level actually. That's depend on the person preference. And then you have to take the two more advanced quantum mechanics classes. So which means altogether four quantum mechanics classes, 4 semesters. Then only you can say, I know a little bit of quantum mechanics still, because based on the Max Planck's and the Feynman explanation, nobody can ever understand quantum mechanics. So if Feynman can say that, then we are nobody compared to that guy. Okay. So if Feynman is a giant, we are like a really tiny, very, very tiny small persons compared to his brain power. Okay. Okay. So anyway, all of those things are background. Okay. Now we'll try to take a look how to understand what we see around us. So which means technically light, now we know, is moving. So the light technically is a EM radiation. So which means three-dimensional wave, okay? Because EM waves are 3D waves, okay? Look like this. That's the energy packet. So we don't care that energy packet concept. What we care is this propagation direction. So if I consider light is moving from one point to another, we know that moving because when you look at any star out there in the night sky, you see something out there means something coming towards you. So which means that is the direction of the energy propagation of the EM wave. So if I consider that energy propagation direction only of a 3D EM wave, then I can treat the light as a ray. So which means we're going to draw arrows to represent the light. So we generally call the optical ray or just ray diagrams later in this in our next chapter. Okay. So ray diagrams mean what it actually show you that energy propagation direction. Technically, this is oscillatory wave in one aspect. And another aspect, that oscillatory wave inside is actually a wave packet. So none of them we considered during our next chapter. We're going to be considering only that propagation direction only. Okay. So which means we can draw a simple arrow to represent a light ray. That's it. Light wave. Very simple idea. Okay. If we have that kind of model to represent the light ray, then by using that model, we can explain very basic observation, like how I observe something out there. If you go in front of the mirror, how you observe your own image inside the mirror, and then so on. That actually purpose of that whole chapter. Okay, very easy chapter. But you need to take a look how to draw the ray diagram. That is actually one of the very important concept of that chapter. Okay. Mathematically, nothing much at all. Only important thing is understanding the ray diagram because it says geometric optics, which means we draw a diagram and then look the diagram to explain everything. Like similar to the vector addition with the graphical method. So in graphical method, you draw the vectors and then use that diagram to add the vectors. So the ray diagram method is also very similar. So we draw a ray diagram and then look the ray diagram, that picture to explain what's really happening. So that's why I generally call the geometric optics. Okay, that's what we actually gonna do in this today's class and the next chapter also. Okay, guys, any question? Okay, now it's really nice model, really nice explanation with the geometric optics because to explain everything to the eyeglasses, to the general microscopic, how the microscope works, or how the telescope works, how you create the image of out there in the telescope, how you do the magnification by using magnifying glass. All of them we can explain by using geometric optics. We don't need the real picture or real real detailed picture of the light ray. It's a three-dimensional electromagnetic wave concept, or if it is more very in detail in terms of basic quantum picture, which is actually a quantized energy concept, we don't need any of those things. So without any of those things, we can just explain everything what we see in general by just using the ray diagram. Okay, that's the plan. So we're going to be investigating, we're going to do in three different optics experiment. This is one of them. Next 2 weeks, we will do another two, okay? Today's experiment, we're going to do we will be investigating idea for the reflection and the refraction. That's the two things we are investigating. Reflection means if you have a surface which doesn't allow light to pass through, let's consider this right side is the completely blocking the light. If I have a light ray, let's consider I have any source of light which can generate a ray, like a simple laser gun or something like that. Then if light ray comes in, that's the energy propagation direction. Okay, that will hit this surface right here. After it hit, generally, we can see this experimentally, this will be reflecting. So if I do a simple experiment to figure out some other information, what's happening, see what happened to my diagram. It disappear all of a sudden. Okay. All right, something happened. All right, so what happening exactly this point right here. So when it hit the boundary, so we would like to understand what is exactly happening there. Then you need couple of ideas. This is actually ray diagram itself. Okay. Then you need couple of other information. This ray we generally call the incident ray. So usually R of in, ray incident. So this is we generally call the R of refracted, R of RE. And in this line right here, which is the line 90-degree angle to the common surface, which is called the normal line, which is 90-degree to the surface. And then if you measure these two angles, then we can find if light ray reflecting back or coming back to the same side, then these two angles, theta I, which is the incident angle, which measured from the 90-degree to the ray number one, which is ray coming in, and then this is going to be theta R reflected angle, which is measured from the normal to the reflected ray, should be equal. So that is we generally call the law of reflection. Theta I should be equal theta R. So all of these we can simply prove by using the geometry. Okay, so that's the other thing. If you make a diagram, simple 90-degree, two lines, then you can prove this. Nothing much to do actually. Okay, so that's the other idea of what we call the geometric optics, because everything we do, we can prove every single thing by using geometry. You learn maybe, I don't know, grade 8, grade 9 level. As I remember, I don't know which level you've done the geometry, and the trigonometry should be grade 8, grade 7 level. Okay. All right, so that's the other, that's why this chapter is so simple, but creating ray diagram is very important. I usually remember every class, 291 class, some student has a lot of trouble drawing the ray diagram, because every single question, quiz question or the final exam question, gonna ask you ray diagram. You need to draw them. When you're drawing the ray diagram, there's a certain important information should be shown. You can't just draw a line, because the line has to have a certain information. This arrow is very important, which direction it goes in. This normal axis is so important. What's the normal axis to the surface? This arrow is so important because all of those are not there. It is not a ray diagram. Okay, if you draw something like this and then say these two angles are same, that is not a ray diagram. Without these arrows and then without telling this is the normal line, so it's not considered as a ray diagram. Okay, so you have to be very, very extremely specific when you draw in the ray diagram. It's not difficult, just practice it. Anybody can do it very easily. Okay, so that's one thing we're going to test it out. So the law of reflection. Any question, guys? So if I want to if I want to do an experiment, then I need a couple of instruments, right? I need a mirror, like you usually watch yourself, and I need a small light ray. Light ray we can generate. We don't need necessarily have the lasers. We can generate the light ray by simply by using any light source. Usually in our lab we have a light box, and that is look like this. We have a box inside. We have a light bulb, the standard regular light bulb, which we generally call the filament light bulb, and then one end it has a small hole here, so that hole can actually generate the simple light ray. Okay, so that's how we actually use if it is in-person experiment. Very simple. If I have the lasers, that's better, but this is good enough, so that will do the job. So then we need the mirror, then we need the protractor, then we need the meter ruler, because I have to generate this diagram myself. Okay, if you're doing it experiment in-person class, we take a graph sheet, place the graph sheet on the table, and then we take the light box, place it somewhere here. This is the hole which actually generate the light ray that should be connected to the power. And then we're going to place a mirror right here. We have a couple of mirrors, and the mirror stand. You can actually hold it. This is a top view, okay? And then we're going to let the light ray hit the mirror, and then we can see the reflected ray. The room should be very dark, because since we don't have lasers, these lines we can't see easily. So we're going to switch off completely all the lights on the room and then cover all the windows. Then it's called the dark room generally. We do all the optics experiment inside the dark room. Then we can clearly see this, okay? Then what we do, we're going to take a different color pencils, and then we draw a line, which actually this mirror is in. Just dotted line to represent where the mirror is, and then a small dotted line to represent this incident and the reflected rays. Then we take off the mirrors and the light box, and then we take the meter ruler, and then we draw these lines with the meter ruler and different colors. Then we put the arrows. This is going to be R in, this is going to be R of RE, and then this is actually mirror. Then we can draw a 90-degree line exactly from here by using the protractor to the mirror. Then we can measure the angle. This guy should be the theta incident. This guy should be the theta reflected. Then we can compare those two numbers. We know those two numbers should be exactly the same. We can just do by using the geometry, by drawing the triangle, and also we can just measure them experimentally and then validate it, okay? So that's a law of reflection. So that's very extremely simple idea, nothing much to do. Any question? Okay, then we'll do law of refraction. So reflection means light come back to the same side, okay? Refraction means in some medias, light can actually go through one medium to another. Then the refraction happens, right? So the light comes from one medium and then it can go to another medium. If you look at it, such an example, like for example, if I have a water container, and then if you put an object like a meter ruler into the water container, and then if you look from outside, you can clearly see at this exact point right here. So it look like it's bended. So that bending nature, when the light go from one medium to another medium, is actually due to refraction. So that's the idea of refraction. So light can go through if the medium allows to light rays to pass through in some medium like glass, water, or any other transparent medium. And such medium, when that progress happens, there should be some sort of bending nature happening exactly in this boundary. There is a reason for that bending nature, because light is a wave, which means it actually doing a frequency or the oscillation per second. So let's draw two lines right here, and then let's consider two light rays, one coming from here and then hit this exact point, and then we'll consider another light ray hit exactly this point. These two are parallel light rays due to some source right here, okay? So if the source is too far away, then usually all the light rays are parallel to each other. So which means even if you have like simple source like this one, we'll consider light ray producing everywhere. But if you go really, really further away, now all of these are waves, okay? So these are three-dimensional wave propagating everywhere around the three-dimensionally. But if you go really further away, then all of these rays, because of the larger separation, it's look like to you comes parallel to each other, okay? So that's why if we have any source out there, like for example, sun rays, when it reaching us, because of the distance, it look like our smaller space, all of these are parallel to each other. So that's why if I have a source right here, this source can generate all the parallel rays towards here, this point, okay? So if I have two rays coming and then hitting the boundary, let's consider maybe this side is glass, this side is air. It can be any medium, doesn't matter. It can be air to water, air to glass. There are different glasses, and even there are plastics which can be transparent. Then what will happen? There is a frequency attached to all of these, and then there is a velocity. Let's consider V1. So the V1 is the velocity inside the medium one. This is our medium one. This is our medium number two. Now, when this is moving from one point to one medium to another, then we can clearly see because of the medium effect. So the velocity of the ray will actually changes. However, frequency, which means how many oscillations per second, will remaining the same. If I assume there's no energy loss during this boundary point right here, each wave carries E equal hf amount of energy. Same amount of energy is actually transferred to the other side. There's no change at all. However, the velocity must be changes. The reason because of the medium effect. So the medium does not allow something to pass through, same as the any other medium. So which means there should be some sort of bending nature. So which means this is the direction where this ray is supposed to go. This is the direction where this ray is supposed to go. Because of the medium change, this ray will bend little bit. This ray also will bend little bit. Now that's bending nature can be different directions relative to the normal line. Okay, this is the normal line. Normal lines means 90-degree lines to the surface. So if the bending nature towards the normal line means this glass medium is actually more denser than the air. So the velocity inside the more denser medium is actually lesser. Because of that, it actually bending towards the normal. If it is opposite, for example, if something moves from glass medium to air, then the bending nature should be opposite to the previous. Okay? So that we can take a look later with our simulator. Now we can do a simple quick look geometrically on this diagram. This is actually ray diagram, all right? These are incidents. You can say ray number 1 I. This can say ray number 2 I. Now this should be ray number 1 R. This should be ray number 2 R. R mean refracted here, and I mean incident always, okay? Now what will happen? We can take a look the some sort of correlation. One of the important definition we're going to use is the ratio between the velocities. If I know the velocity of the light in air, generally, air means generally we call the free space, which means the space is not much affected to that light ray speed. So that speed is generally we call c. That is a number I used earlier, which is about 2.99 10 to the power 8 meter per second. Okay, so that's a number calculated from the Maxwell's theory. So that's true because that number is already measured last 100 years many times. Okay, so that's not just a theory, that is actually true. Nowadays people can measure that number with really good accuracy. Now what we're interested to see, some sort of correlation within this bending nature. Okay, to understand that, we can use a ratio between the c divided by the velocity of any medium. That ratio is actually called the index of refraction or refractive index. So what's the index of refraction or refractive index means? Index of refraction, or sometimes it called refractive index. What does that mean? The effect of mediums to the light ray. So which means this is a unitless parameter. Okay. So what it's telling you, how much the medium effect, like for example, if I calculate this for glass, then you will get this number something like 1.5. Then by knowing that, by knowing C is 2.99, we can calculate what is the speed inside the glass medium. Then the glasses are a lot of different mediums. Because of that, this is just rough number. Actually, depending on the type of glass, this number can varies from maybe 1.4 to maybe 1.7 or 1.8. There's no particular number. Okay, I just pick that number. For water, if I calculate this number, that's going to be 1.33. And then so on. You can see the minimum value for n is actually 1, because whenever the v is equal c, then you will get the minimum value for n is actually 1. So which means the n can have any number above 1 depending on the medium. So more denser the medium, more barrier to the light propagation inside the medium, then I will get n is larger. So the highest value of n we can found inside the diamond. That's about, as I remember, 2.2 or 2.4. Okay, so that's the highest number, because the diamond is the most beautiful one if you look at it externally. The reason there's a lot of scattering effect inside the diamond. Okay, that's the reason technically. So that's the highest value we can get. It's transparent, but it's not transparent like the glasses or anything. Okay, that's the highest value we can get. Water is about 1.3, and the glasses can vary this number maybe from 1.4 to 1.8. Generally, we can get 1.5, and then so on. Okay. So there's a minimum value, but the maximum value, we can't say anything. Like for the friction, for example, uh, friction can be 0, but the friction can be any number above that. So there's no any fixed value for friction. Okay, depending on the surfaces, this is also same. Depending on the boundary, what are the material mediums are, n value can be anything. It's a unitless parameter. Okay, so we can take a look with that definition, some sort of little bit of geometry here. If I make a two other lines, let's draw a line right here, 90-degree line from this point A to here, and then we'll draw another line from point B to the ray number 1. So if I draw that, so this is velocity v1. So the inside this will say velocity of the light ray is v2. So which means this part right here, we can say that displacement, let's say for example, some delta of d, that displacement we can write v1 times t. Within a certain time period, how much distance is traveled. Now, within the same time period, how much the distance traveled, right here, this part, we can write v2 times the t, because it exact time period, it is less distance now. The reason, oscillation remaining the same, which means the frequency remaining the same. Now it look like shrink the waves. However, wave is actually traveling certain distance. Now it is less because of that bending nature. Okay? That's why it actually bends. So keep the same frequency. It has to bend, which means it has to decrease the wavelength accordingly. Okay? Because the velocity is affected now. So remember, this formula is still valid. Okay, V is equal lambda F is still valid. So which means if I want to keep the frequency the same, then if velocity is decreasing, lambda also should decrease. Okay, so that's the idea. So that's why the bending nature happened towards the normal. So if you take a look, the later we will take a look that if I take a look the inside the glass medium to air, then the bending nature should be against of this particular picture. Okay. So then we can take a look, little bit of geometry here. This angle we know should be the theta I, which means the incident angle, measuring from the normal axis to the ray, number one. Then this should be the theta R, that is measuring from the normal line to the ray number one, but refracted ray. So by geometry, we can identify a couple of things, right? This angles right here should be theta I. Since this is 90 degree, then this angle right here should be theta R. Then let's consider this line is X. Then you can write, for example, trigonometric parameters like sine theta for both the triangle, upper one and the lower one. So if I do that, so let's write the sine of theta I. So that should be then Vi times the t divided by the x. Let's write the sine of theta R. That should be then V2 times the t. Let's use V1 and V2 times the t divided by the same x, because x is actually the hypotenuse for both the triangle. Now we'll divide these two. If you divide these two, you will get sine theta of incident divided by sine theta of refracted. I have V1t divided by x divided by V2t divided by x. So the t and x cancels out. This is going to be simply V1 or V2. That I can simplify a little bit further. So we can simply say sine theta I 1 divided by V1, which is equal 1 over V2. Sine of theta 2. Then we'll multiply both sides by the speed of the light in air or the free space. Then this part right here is actually the refractive index of the medium one, because remember earlier we defined the refractive index. So this should be for medium number one, sine theta I. So this should be for medium number two, sine theta R. So now this is actually generally what we call the law of refraction, or generally also called the Snell's law, because he's the guy who actually did this geometrically. So that's the idea of geometric optics. You can see everything we can actually prove by just using the geometry which we learn on grade 7, grade 8 level. There's nothing else here. Only thing is little bit of information we need to understand what's really happening when this process is there. That's the extra information. Other than that, it's nothing any serious matter or anything needed. Okay. So that's the nice thing in this chapter, but you need that extra information a lot, because if you don't understand really what's going on there, then the geometry itself not going to do anything. Okay, so because you need a lot of detailed information, that's the part you need to really try to understand. Okay. All right, guys, any question? Okay, that's the law of refraction. That's what we're gonna test it out next. The first one is we're gonna test it out the law of reflection. That's nothing much. Theta is equal to theta, very simple. And then by using that concept later in next chapter, in the next week, we will take a look how the image are forming. Okay, so we will talk about that next week a little bit in detail in our chapter work, image formation of the mirrors and then so on. So then we will get a better understanding why that concept is so uniquely useful and important. But today's lab is not about images, just to understand that process, what the reflection means, what the refraction means. Okay, we are not talking about images yet. We will do that next experiment. Then we can test it out this, right? Now, if I want to test it out, I want to design an experiment. So what I need maybe a glass piece. This is again, if I do this experiment in person. So what we do usually, we take a graph sheet, put it on the table, and then we have small glasses like glass block. You can see on the top, and then we place on the table on top of the graph sheet. Then we take our light box and then which can generate, this is connected to the source, this can generate a small light ray. So we are doing in the dark room, everything, okay? So the light ray will hit the glass, and then after it hit, you can see now this is the normal line. We don't have that normal line yet, okay? But if you observe from the top view, you can clearly see this is where it's supposed to go. That's where it's supposed to go. That's a straight line where it's coming in. But from the top view, you can clearly see this is bending. You can't see that part, okay? You can see that part, you can't draw that part. So what we do, we draw these lines very small dotted by using a pencil. And then from here, you will see again light rays going out. We're gonna make a small dotted line by using the pencil. Then we draw this outer line by using a pencil, this outer line of the box that we need. And then we take off the light box and the glass piece, and then we're going to create these solid straight lines by using the meter ruler and the different colors. Then after you create this, then this is the diagram we have. So then we can actually connect these two, and then you can clearly see, if you look at it here, you can clearly see two interesting features. So this is coming in, this is inside what's happening, this is going out. Now this is the theta I incident angle, always this angle measured relative to the 90-degree angle. We can draw that 90-degree lines exactly at this point A and the point B here. Then this part right here, if I zoom in, this part, okay, point A, if I zoom in, you will see something like this. So the light ray coming in, and it's going to be theta I. So this is bending. So this is where it's supposed to go. This going to be then the angle of theta R. That bending nature you can visibly see, but we used earlier is true because the glass is more denser medium than the air, bending nature towards the normal. So this is the normal line. Now, if you look the same at this point, point B, then you will see the opposite. So if you look at it, what is happening, point B, light ray comes in like this. That is incident, that is inside the glass, okay? And then this is where it's supposed to go. And then this side is air now, this side is glass. For this case, this side is air, this side is glass. So the air to glass, glass has the higher refractive index. So in this case, glass to air, glass has the higher refractive index. Now you can see the bending nature is actually opposite. It bending away from the normal, okay? This is still the normal line. So that you can really see, okay? So in real life experiment, from top view, what I draw here is actually what you're observing. Everything is on the table. You look from the top, then you can exactly see that it is, okay? So it's not really a model. It is actually what really happening in the nature when the light ray hit the surface. That's why we don't need that very fundamental reality of lights, which is actually oscillating EM wave or quantized energy moving. Those concepts, we don't need to explain general things what we usually wanted, like how the eyeglass is working, how the telescope is working. Those things, we don't need any of those real reality of light, okay? So we just need that ray nature, which means where the propagation direction, that's enough. That is actually this arrow represent. So then we can measure this, right? So I can measure theta I and theta R. By measuring that, I can actually test this N1 sine theta 1, which is equal N2 sine theta 2. That is Snell's law. I can actually investigate that. So that's the idea on our experiment part B. Any question, guys? Okay, so that actually covers a lot of things for next week lecture too. So I can speed up that to save some time a little bit there. This is a longer chapter, has a lot of things. Part one of the chapter is investigating these ideas, reflection, refraction, and image formation. Then part B of the chapter is actually investigating optical instrument like the telescope, which is a combination of lenses, the simple telescope. Okay, so but how can I explain by using the ray diagram image formation of simple telescope? If I have two lenses together, then if I have a microscope, which is again the two lenses together, how can I explain the process of that by using the ray diagram? So that's the part B. So hopefully we can finish everything since we covering a lot of background information here. Okay. Then very last part of the lab, we can investigate very specific result of the refraction, which is called the total internal reflection. Total internal reflection is actually specific result of refraction technically. You can see the reflection term is there. You will see it see in a bit why the reflection term is there. So what we're going to do, we're going to send a light ray inside the glass medium, which means higher refractive index to the lower refractive index. This is here N1. N2 is larger than N1, okay? Because we know V2 is less than V1. This side velocity V1, this side velocity V2. And we know N is equal C over V, okay? That's the basic definition of the refractive index. Which means if I send the light ray, let's consider from the glass medium to there, then you should see a bending nature. This is where it's supposed to go. Now it is bended. Bending is now should be away from the normal axis. So that should be like this here. Okay. Any question? Good. So the bending is away from the normal axis, right? Which means this is the normal lines. Observe very carefully, okay? The basic ideas. That's a normal line. Bending should be away from the normal axis. Mean this should be right here. So it's going more away from the normal, okay? This is where it's supposed to go relative to that line, and then relative to the normal, it should go more away. So now if I change this incident angle, this is the theta I, this is now the theta of R, okay? Now, if I slowly increase this theta I, you can see what will happen. This is where it's supposed to go. Now this is where it is bending. Now the bending is actually more towards the boundary. Then there is a very specific point we can find. With the incident angle, very specific point, that bended ray is exactly on top of this line. So you basically not going to see it. So basically it will look like the refracted ray disappears for a moment. If you increase the incident angle, now this is the incident angle, we call that a specific point is the critical point. If you increase the incident angle anything more than that, anything more than the critical angle, then you can see the refracted ray now appear back inside here, inside this medium. Because if I have a little bit of more angle here, it has to bend further away from the normal. So it's going to be coming back towards where it initially started with. So that is actually reflected ray, right? So that is why it's called the total internal reflection. Because of the refraction effect, you can actually generate the internal reflection. It coming back to the same side, that is reflection. So this is a very unique application. There's a lot of different application. One of the unique application is the fiber optics. So you can see how all of these are actually connected. Okay. So the fiber optics, we know now the highest speed, the normal regular broadband speed we can get from the fiber optics. Now that fiber optics works under this condition because the electromagnetic waves are actually working similar to this light rays, which means if I have a mirror, a tube created by a mirror, then if I send the wave from here, then if that wave hitting this boundary, any angle larger than the refractive angle which we describe here, the critical angle, then this should be reflected back again to the same side. So this is created, this tube is actually then the mirror tube, okay? Fiber optics means. Then I can send this wave inside by using that internal reflection from one point to another. That's a fiber optic communication very basically, okay? So that is not, things are very complicated than that, but that's what really fundamentally happening. So which means I can send the wave from one point to another by using that total internal reflection. Because of that, the speed of these waves inside here is very close to light speed. So that's why you can get a higher speed if you have a fiber optics communication line than regular copper wires. Because if you have a copper wire, it not work under this condition. Copper wire propagation is electron moving from one point to another. That you cannot achieve such a speed. Okay? So the standard broadband lines are copper wire lines. The fiber optics lines are generally look like working on the total internal reflection. So you can get a really high speed if you have a fiber optics line, okay? So that works under this condition. If you apply Snell's law exactly at this critical moment, at the critical moment, what really happening, I have a glass medium right here, air medium on the top. This is going to be, we'll say N2, this is going to be N1. I did it other way around earlier. This is I put N2, this is I put N1. So if let's consider this is AR means N1 is equal to 1. Let's write it down. Glass medium N2 is just N, okay? Because of that, if I consider I have a critical incident angle, which is theta of C, then our refracted line should be exactly on top of here. So this 90 degree should be the theta R, which is 90 degree now. This is actually the theta I, which is the critical angle. Let's apply Snell's law exactly at this location, which means in 1, sine theta 1 is equal in 2, sine theta 2. In 1 is actually just n right here, which is coming in. And then sine theta 1 is sine critical angle, n2 is 1, and then sine theta 2 is 90 degree. That will give us really nice equation to work under this particular condition, which means n times sine theta of critical is equal 1. So the critical angle theta c is actually sine inverse of 1 over n of any medium. So that's very, very useful equation, which means if I know the medium like glass or whatever the medium is, then by knowing that refractive index, I can calculate what is incident angle should be if I want to generate total internal reflection, which means getting the light back into the same medium. Okay? So that's our last part. Okay, guys, any question? Okay, that actually covers a lot of things which we needed next week, Monday. Okay, be mindful of these and try to review them before next class. That will be useful. We can save a lot of time from this part because this is not so important. What really important in that chapter is image formation and the lens combination, because that way we can really see how the geometric optics in real application perspective. This part is like more definition and then background, not much really interesting. Okay. So let's do an experiment to confirm all of these ideas. So that's actually today's experiment is nothing much to do in terms of more detailed experimental analysis or anything. Basically, we're going to investigate the validity of those things. Okay. So you can go into the lab manual, has all of those information which I discussed, and then it has one little bit of extra information how the image formation happening on the plane mirror, that also you can read later. That we will go through again maybe on the next experiment too. Okay. And let's scroll down to the simulator right here on page number 3. And it should be look like this. You can use single light bulb or RGB light bulb. The first part is we try to observe this color mixing, nothing much to do. So it's a simple idea. I can put a different color lights and then see what the resultant color is. Okay, so that's it. So which mean you might not be able to see these lines because it's under black background. So right now I have a blue light. And if I combine with the green, then I will get a different color. Okay, that's the idea of color mixing. So which means technically inside the white light has all of those colors. Okay, white light is not really a color. It actually mix of all the colors. So I have all the rainbow colors there. That's why you don't see any colors because all the colors coming into your eye. So our observation is actually depending on our nerves, right? When you get the color into the eye is actually generate a signal, then our brain has the data storage. So telling that this signal is actually this color. So that's how we identify. If the data is not there, then we don't know what we're really observing. So it's based on the data. So the data is created again ourselves, right? So from childhood, slowly around you actually generating that data. So everything what we do day-to-day life is based on that data, not the real thing what's happening in the universe. That's extremely important. When we go into the quantum mechanics, then you will see a really, really important correlation between them. What we're really thinking as I am, or what you're thinking as yours, or what you're thinking as mine, or all of those ideas is actually just an illusion. Nothing exists like that. So think about that very seriously. And then if you want to talk about very into a different angle, you can stay after the class. This is not the right time to talk such details, okay? But the reality is that. So the our database is actually generated database. It's not really coming from elsewhere. It's not somebody is put that database into our brain. When you're born, we don't have a database when you're a child. So then that database is generated when you're slowly growing up. Maybe some data available because even if you're in the womb, you can hear sounds, things like that. You can't see colors or anything, but it's still the sound and senses you have a little bit of information, but not much. Everything else after we born into the world is actually generated around us, which means depending on where you grow up is actually has a huge effect what you're doing right now. So even though we don't think about it. So that's where we need to keep the open eye. If you have a close-minded, then you're not going to able to absorb something new and then grow. This is for general idea, okay? So because sometime depending on how you grow up, how we grow up, sometimes we have that close mindset. I'm not open to discuss this and that. That is really not meaningful because nothing exists like that in this universe. So everything is we created this illusion around us and then we try to stay inside that bubble thinking that this is the reality, but that not something exists. When you learn the quantum mechanics in really detail, then you will be able to understand that. Okay. All right. So that's the idea again. So we understand it's a blue because our brain says it's blue, right? So if we are in the different universe, maybe that blue color is still there, that energy and things like that, because the light has those things. But the word we're referring may be a different thing. Okay, so that's the idea. So you can get it into this into very different angle, depending on the interest. That's what the neuroscience, things like that actually doing nowadays. And if I put it into the red also, then I will get a completely different colors. If I put it all of these into the maximum intensity, then I will get something like colorless. So that's the idea of color mixing, nothing much to do in terms of calculation or anything. We can report those observations right here on table A, okay? Table 1. This word you may have to edit, I think, due to some mistake, the green word here, I think there's a typo. Just change that into green on row number 11. and then mix the colors according to these and then complete this table. That's going to take only just few minutes. Any question, guys? So this is maximum intensity. All the colors are put it in, because if you do in real life experiment, I don't have intensity variation there. I have only these filters. So we're going to put the filters and then take a look what we get. That's why I'm going to put the maximum intensity. Otherwise, intensity-wise, you will see slightly different, but I cannot do that observation in real experiment, okay? Then we'll do red and blue only. Get rid of the green. Then you can put the colors you see. And then you can put red and green. And then get rid of the blue to the maximum intensity, okay? And then you can do green and blue. Get rid of the red. And just write what you see, that's all. Which means in between we have like infinite number of color mixing technically, right? Because this is depending on the wavelength and the frequency. So which means if I small amount of change these frequencies, you can see the observed color is very different, right? So that's why in general we have certain colors in the spectrum, but technically by mixing them we can get various other colors, okay? All right, so that's very simple, just observation, nothing much to do. So the other simulator which we really needed for the experiment is actually this one, page number 3, just a simulator right here at the end. Okay? So that's a simulator we really need for the rest of the experiment. Just click on that. It has like 3 different options. So the click on the last option called More Tools. So that's the one we need. Any question, guys? Okay, so then let's take a look what we have here. So we have a white background and the purple background. Uh, White background is the air, and I have a laser gun here. You can see when you bring the cursor, you can click and drag it like around here in 90 degree. So which means if I click this and then switch on, then you can see I have a light ray, a small laser ray. So that hit the boundary here, depending on the two mediums, I can see both reflection and the refraction. Okay, if the medium is like glass, then there's a small part of reflection here, then most of the ray is actually going in. So that is a refraction, okay? So I can study both by using this simple setup. So I can study both reflection for the first part to understand the law of reflection, then the later two parts for to understand the refraction, okay? So then you can see other couple of information on the top. There's a ray, or you can see it as wave nature, for example. We don't need the wave nature, but you can observe that when the light ray hit here, if you look at dark color and the bright color spots, separation between them is actually related to the wavelength. So you can see when it is go inside here now, inside medium is actually much higher, or in terms of refractive index. Because of that, those separations are shrink now, which means wavelengths becomes smaller. The reason the velocity becomes smaller. Okay. Let's put that into air, for example. If that happens, then you can see it continuously going in. So now my incident medium is air. Then the other side, there's no any separate medium. You can see that medium is also air. Then it is going in directly. Okay. There's no any medium effect. There's nothing happening to the ray at all. So let's put the glass medium. Then you can see that reflection part that is important. So you can put the custom and then increase this refractive index to the all the way to the higher. That also okay. for first part, but I'm going to use the glass at about 1.5. Okay, so we'll get rid of the wave nature. We'll go back to the ray. The color of the light, I'm going to keep it red. That's easy to see. If you want, you can change into blue. That's fine with me, nothing wrong. But I'm going to keep it red because most of the general laser guns we can buy also has the red. Okay. Then we have a couple of other information. The top small part on the right-hand side is the refractive index and the medium. And then left-hand side bottom corner, you can see a protractor I need because I would like to measure angles. And I can measure, for example, intensities of these lights if I want to. And also I can measure wavelength and the wave frequency by putting into like similar to like observation we do with the oscilloscope. We don't need actually any of those things for this experiment. And also I can take a look, for example, the speed of the light I can measure with this item. This is in the AR1C, 2.99 10 to the 8. And then inside the medium, you can see 0.67. It reduced. So that reduction, that ratio, C divided by 1.67 times C is actually generate the refractive index about 1.5. Okay. So that's the idea. We don't need those three technically for the experiment. So we just need the light ray and the protractor. Any question, guys? Okay, we'll bring the protractor midpoint right here. Gonna align with exactly where the light ray hits, right? Then I would like to measure incident angle. We can start from somewhere like maybe 20-degree incident angle. So the protractor has 0, 30, 60, 90 here, which means each of this little bit larger line is 10 degrees. The smaller line is 5 degrees. And between each of those lines, you can observe all the way down to about 1 degree measurement. Okay. So the accuracy is about, which means half a degree in this protractor. Okay, guys, so you may need to zoom in a little bit if you want to really measure the angle as accurate as possible. Okay. All right, any question? Good. Okay, so let's do the measurement then. Little bit of, we'll start from like 20 now. This ray is little bit thicker. That's error part, the human error part attached with this measurement. Since the ray is thicker, when I measure that, I need to measure exactly from one particular side of the ray. So I'm gonna align this left side of the ray to exactly 20-degree line. Then I'm gonna measure same side of the ray on the other side of this reflected ray right here. Okay. Then I can measure it as accurate as possible. Also, you can do exactly midpoint of the ray pass through the 20-degree line and the midpoint of the ray on the other side. Okay. So we will get slightly off values. That's okay. That's what really going to happening if we really measuring this in-person classroom. Okay. Now that this is the top view. If you're really doing this in-person class, all of these going to be on your table. When you look at it from the top, that's what exactly you're going to see, except this rays in red color. In our lab, we don't have these lasers. We have just a light box. So it's going to be just colorless or the white color. Okay. All right, so let's do a couple of measurements. We'll start from table number 2. Table number 1 you completed right now. Nothing much to do, just the mixing. So we'll do air to water angles. We'll measure incident degree angles. You can find the degree sign inside the symbols and then insert the degree sign. And same degree sign for other two also. So that's our unit technically, okay? PD doesn't have any unit. You can put the percentage sign there. Okay, guys, question? Okay, so that's it. It's very simple measurement. So I need to measure the incident angle. It says to use these numbers, we'll use them. 20, if I put it into the 20, what I see on the other side, you have to measure as accurate as possible. Depending on how you actually align this. Okay, I try to align this exactly one edge pass through the 20-degree line. Then I'm going to measure the same edge on the other side. Okay, that's the plan. If you zoom in your picture, you can see it clearly. I don't see exactly 20 here. I'm going to see about like 21, roughly about 20.5. So I'm going to have a little bit of error. That's okay. That will be our measurement error. One of the reason going to be this midpoint may not be correctly aligned, midpoint of the protractor. That's one reason. But we will keep it like that. That definitely the reason in my case. If you look from the very top right here, you will see that error. Right here on the top line, it's not properly aligned, but I'm going to keep it like that. That's going to be the similar errors we will see if it is in-person experiment. Okay, that's it. Then you increase this 10 degree at a time. 30, I'm going to still keep the left edge passing through the line, okay? And then I'm going to measure on the other side. I see it like 31 on other side. And then 40. And just the human error, okay? It's not really any error because of the geometric optics scenarios. It's actually human error. Okay? Now it's fairly very good alignment on other side actually, 40. Okay, guys, any question? 41 on other side, and then 50, and then 60. That's it. Look like 450.5, and then 60, about 60.5, and then 70. That looks almost 70, but I'm going to measure it to 70.5. Yeah, we are doing AR to glass. Okay, we should use the right side of the table number to correct. Yeah, so just you can use the column number F. Okay, yeah, that's correct. Okay, please do that. So the column number F on table number 2, because it's asking you to do air to water and air to glass. So right now we are working on air to glass. Okay. All right, then you can compare this. It's very simple comparison. Percentage different. Okay. So open bracket ABS, open brackets, ABS, open brackets again. Doesn't matter percentage different which comes first because the denominator is the average. I'm gonna compare incident and the reflected divide by open bracket twice, because denominator should be the average of these two numbers, divide by 2, close bracket again, multiply by 100. So that is small difference is actually because the error we created ourselves. Technically, there's no any errors or the wrong in the real theory. Okay. All right, so the PD equation is the only one we need in terms of equation here. And then you click and drag. All right, guys, any question? Okay, so we can test it out that for the different medium, we'll select the water. For the second medium, then it's light blue color, okay? And then you check it out again. Very simple idea, okay? So let me take a look one quick thing. We are supposed to do, I think, the group lab report for this one. Optics number one is individual lab report, okay? So we don't need to do a group work. Today we'll do a group work for next lab. That should be fine. So we'll continue this here. Okay, so let's go back to the 20 again and then start from there. I'm going to use a one edge, but you can use either middle of the ray or maybe one edge, doesn't matter. And it's the same exact thing, okay? If you zoom in the picture, it's easy to measure. 20, it's about 20.5, very similar to the last one. 30. So if it is a real experiment, we're going to need fairly decent amount of time because you have to really uh, draw diagrams, which mean you can't just proceed. Every case you have to draw small lines to represent all the rays. And then after that, you have to create that diagram into a solid line, then draw that 90-degree line, then only you can actually do the measurement. Okay, so it's a little bit longer process, need good amount of time. So this is very simple because of the simulated result. Okay. 40, which is about 40.5, I'm going to use that error purposely. And then 50, incident angle, 50.5, 60, and then 70. I'm going to keep that error 60.5, very close to the perfect number. We will keep the error and about 70.5. And then again the PD, same function, equal open bracket ABS, open bracket, different between the numbers, divide by average between the numbers, okay? Because we're doing PD, not PE, okay? About the same error, percentage error values, because my reading error is about the same. Very simple setup, very simple experiment, I think, very simple to do. We'll take a one screenshot of that one and the one screenshot of the previous one and leave it here because you need them for your lab report purposes. All these pictures should go into your procedure section. Okay. We'll take one for this one. Okay, all of this area for the color mixing and make it smaller. That's going to be our figure one. And one another picture for the other simulator. That is a simulator we're going to use throughout the experiment today. So one is enough for that. That should go here. Take the picture, represent all of these information, medium information, protractor and everything, and make it smaller. That should go here. Okay. And you need to name always any pictures as figures. Figure number one, we can name it color mixing simulator. And this one we can say reflection and refraction simulator. Okay, make sure you name them properly. All right, guys, so that nothing much It's very simple observation. Uh, if we're doing this in-person classwork, actually that ray diagrams we're going to attach into our lab report, but in this case, no meaning doing it because we are not really creating ray diagram, we are observing them, not much meaningful. So that's why I did not add that part here under the table. Otherwise, if it is a real experiment, that ray diagram is very important because you have to first draw the ray diagram, otherwise we can't do any measurements there, okay? Okay, guys, any question? Any problems? Okay, let's make a quick break here and then we'll continue from there. Uh, let's take a maybe quick break here. You have, okay. Let's continue. So let's move into the refraction. Reflection means all the light coming back to the same side. There's no anything goes in, okay? So refraction means there can be reflection too when the refraction happening, but we are not interested what is coming to the same side. What we really interested is what is going in, okay? All right, so let's take a look. We can use the same simulator and then we can investigate the same air to water and then air to glass. Since we have the water already on medium 2, we'll keep it. And medium 1 is air. We'll keep the same protractor here. We can now measure incident angle starting from 20 degrees again, but we are not interested this ray which comes to the same side. What we interested is actually the ray which goes into the medium, okay? We are interested is this ray. So which means we interested this angle about 20 degrees. Try to zoom in the picture and then measure it as accurate as possible. And then we interested to measure this part of the angle. That now about, we are trying to measure to this edge, okay, inner edge, okay, I'm using. So if I use to the inner edge, it's about 10, about 15, close to 15, maybe 14, 14.5. Okay, try to get it as close as possible. All right, guys, any question? Okay, we can use the same degree units here. Actually, unit is already written. You don't need to write that again. And refractive index is unitless. So let's consider 14.5. Let's check it out with the refractive index. We know the refractive index from Snell's law, which means n1 sine theta 1 is equal into sine theta 2. If I write that for this particular case, n1 sine theta 1 is equal into sine theta 2. This is medium 1, which is air. This is medium 2, which is water. So which means I'm interested to calculate the refractive index for the water because Ai N1 is 1, right? So the water refractive index is equal, N1 is 1 sine theta 1 divided by sine theta 2. So let's do that calculation. Equal sign, sine parentheses, Excel can read only radians. Because of that, you have to use every time we do in any calculation with the trig function, make sure angle degree given in radian. The Excel cannot read the degree values directly or cannot give out the degree values directly. It can do only radians, okay? So radian commands theta 1, close bracket twice, divide by sine, open brackets, radian commands theta 2, which is the refractor, close bracket twice, hit enter, 1.37. We are expecting about 1.33. So it's close enough. The error is because my angle error. That's very normal, okay? So Any question, guys? Okay, then that's it. You just continue through this table, because the table calculation is not what really interested. We would like to make a graph to do this measurement. Because if I look this part of the equation, then I can write, for example, sine theta 1 is equal n times sine theta 2, which means sine theta of incident is equal n times sine theta of refracted. So I can make a graph if I put this part right here into y-axis, this part right here into y-axis, x-axis, then I can make a graph y equal mx. Slope of the graph should be the refractive index, right? So that may be very nice to take a look that way. So I can put the sine theta incident here, sine theta refracted here. You will get a data set look like that. Then we can ask Excel to feed the data. So it will tell us what the equation, it should be y equal mx type. Slope of the graph directly should be the refractive index. So because of that, we'll collect a data set, which means by changing the incident angle, we'll remeasure the refractive angle few times. And then we can calculate each data point at a time. And also we can take a look how the graph look like. Okay, that will be very useful to see how the average behavior look like. So let's do both of them. Any question, guys? Okay, then let's continue. All right, so I did 20 degree. All I need to do is increase the incident angle slowly. We'll do 30 degrees, 40 degrees, and then so on. Let's say 30 degrees. I'm getting like close to about 10, 20, maybe 21 roughly. I'm going to keep that error purposely. That doesn't matter. We're going to see that such errors in real life experiments anyway. Then 40, getting about 25, 26, 27, and then 50, incident 30, 34, and then 60, incident about 35, 38, and then 70, incident 40, 44 roughly. Okay. And then I can click and drag this. That will tell us the refractive index. I need the one function here. This is going to be the N for water. All right, guys, question. All of the numbers are good except one or two places I have a little bit of more error. I got 1.4, 2 positions because my reading error for the refractive angle, okay? All the other numbers are good. Okay, guys, any question? Okay, then let's do the same one with the different medium, which means I can change the medium 2 into a glass, 1.5, and I can do the measurements again, starting from about 20 to 70 again, okay? Twenty, we're getting about 14, and we'll do the function again here, equal sine radians incident angle, divide by sine radians, refractive angle, and I'm expecting 1.5, I'm getting 1.41. Any errors there, again the reading error. Okay, it's going to be in for glass. And then you continue 10 degree at a time, increment of 10 degrees. Okay. And 40, 50, 50, about 30, 60 and 70. Okay, so looks good. One or two numbers are a little bit deviated. 1.41 is the most deviated one because we need about 1.5. All the other numbers are much closer. Okay, guys, any question? Be careful with that function. It has the radian command inside the signs. That's important. Excel can read only radian values. It cannot read any degree values directly. Okay. Okay, I think no problems. Any question? Okay, let's do the graph then. We know it works fine. The ratio, which means the Snell's law, is actually working fine. To make the graph, I need the sign values separately because I need to make a graph, sign incident versus sign refracted. So we'll make those in here. So we'll do the sign radians of these values and then click and drag. You can keep maybe few decimal places more because I'm reading to three significant figures. I should have everything in three sequence. Okay. So that is the sign function for incident for case 1. I can add that also on the top of this table has a little bit of a space. Or I can add just below here. Should be fine, I think. It's going to be sin theta incident. Sin theta in and sin theta RE. There's no units for the sign, it's just a number, okay? Sin parentheses radians and RE for case water. And you have to do the same for the glass, okay? Any question, guys? Okay, and you need at least two commands. One is sin theta in and other one is for sin theta RE, okay? At least two of those commands just under here. So this should be then sin theta, we can say RE. Okay, so after you get those sign values, then we can make the graph. Any question? Okay, then let's make the graph. So I need the graph sheet first. Insert charts, scatter plot without any data. Double click, right hand side top corner, select data, then add. I can do series 1 for air water. I'm just gonna say water for that. And x values is the refracted sine theta. And the y values is the incident sine theta. Click OK. And then you can add the other series. You can click add again. Then we'll add the glass into the same graph. X values refracted for glass, Y values incident for glass, sine values. Click OK again. Then we can do the editing for the, there should be two different data set, okay? Go in two different colors. Then put the axis title. I think this everybody now much familiar, but if you have any difficulty, always ask, okay? You need to put the trend line for both of the data and chart title, axis titles, and then after that you have to go into the each line and then right hand side format trend lines. Last option from the very top, scroll down, click all these three options at the end. We would like to see the slope of the graph and the R square, because R square going to tell us how good the data fit with the trend line linear. And I have to do it twice because I have two trend line here, not one. Okay. So I need that equation, two of them. Slope of that equation, showing you y equal mx type equation, number in front of x is the one should be representing the refractive index for that medium. Okay, guys, any question, problems, any concern? Any question, guys? Make sure you add the axis titles accordingly and the graph chart title, and also you need to rename this as a figure number 3. This is sine theta in versus sine theta RE. Okay. R square good, very close to 1. And if you look at the number in front of x that represent the slope, that actually should be the two refractive indexes. Water 1.5, I'm getting 1.5021. Sorry, the glass, I'm getting 1.5021. Water 1.33, we expecting I'm getting 1.377. So a little bit much error in the water case. I think I did a little bit of error with my measurements, angles that I can see clearly here. Couple of decimal, couple of numbers are way off. That's why. Otherwise, both numbers are fairly close enough. Okay. Any question, guys? Okay, then let's move into the little bit of analysis with the slope. water refractive index calculated average I can do from table number 2 because we calculated table number 3 refractive index we calculated few times. For each incident angle we'll take the average of them, about 1.38, and we can take the average of glass also from table 3. We did the 6 times the calculation, so we'll take the average 1.49. Those functions should go here, at least one of them, because average is the same function. I'm going to put refractive index in uh, calculated AVG for water only here, because it's the same function for the other one. And then refractive index from the graph is actually slope of the graph. There's nothing to calculate. So slope of the graph for water, which is the blue line, 1.3778. And for the glass, 1.5021. Now, if it is rounding automatically to two decimals into 3 sig figs, these are calculated values. It's better to keep 1 or 2 more extra sig figs. You can highlight that area and then edit the sig figs by using home menu bar middle number area and a small left arrow. Okay, I'm going to keep like 2 decimal place extra, but don't keep too many. Okay, we don't need like 10 decimals there, 1 or 2 extra than which is needed. Okay, we'll add that information here in from graph. Water from graph, which is equal slope of the graph. Okay. All right, then let's compare percentage error. Technically, we can do percentage error or percentage difference, because if I want to do percentage error, I should really compare that to the real value. So since if I want to do the percentage difference here, because I have two numbers from the graph and the calculated value directly, both are experimental values. So we'll do percentage difference here instead of error. Okay? Then I can compare those two numbers, not to the real value, graph value, to the number I calculated directly, average value. So equal open bracket ABS, difference between the numbers, and then divide by the average of the numbers. Okay, which means adding and then divide by the same. Okay, guys, any question? Okay, make sure when you do the PD, don't keep too many sig figs, PD or PE at any given point. Just keep only like 2 visible significant figures. We don't need too many sig figs for any of the PD or PE. Significant figures does not reflect anything on error calculation. Okay? So that basically telling us whether the measurement is good or bad. Okay. Since I compare calculated and graph values, my percentage error are lower. But if I if I compare these two to the real values, then I can see the errors little bit in detail. For example, I can do PE for the average. Okay, let's do that separately. On column number F, you need to create that column. Okay? Column number F, column number F. For the table 5, let's compare PE for cal average. If I do in that, we know for the water equal sign, parentheses ABS, expected value 1.33, calculated average of 1.38, divide by 1.33, close bracket, multiply by 100. That error is little bit larger, right? That's what we're expecting from those two numbers. Get rid of all the decimals, show only one decimal, two significant figures. Compared to the real value, it's a little bit larger. For glass, if you do the same, open ABS, open brackets, expected value 1.5, calculated value 1.48, close bracket, divide by 1.5, multiply by 100, it's about 0.8. That is much closer, which means my measurement is actually much better in that case, okay? You can add that column and then make all the lines are visible. I'm going to add this PE. That is PE, we calculated at least one of them, PE for water in here. Okay, that is extra calculation I did because PD is good because I'm comparing my calculator to our graph, which we created based on the calculation. So the PD is very small then because numbers are almost similar. But if I compare that to the real values, then I can clearly see when I do the glass medium, I did good measurements. But if I go back to the water, my measurements are a little bit off. If that error is higher, then I can take another data set very quickly with careful measurement. Then I should be able to reduce that all the way less than 1 definitely. This is a simulated result. So we should get usually very small percentage errors. Okay, guys, any question? Okay, then let's continue in next part. We can take a look the unknown medium. For example, if it is in-person work, we have glasses which are transparent, but different type of glasses. So some glasses refractive index given, but every glass refractive index is not 1.5. Depending on how they made the glass, it can be varying from maybe like 1.4 to 1.67 or so. We don't know. So we can actually find, right? If I know any transparent medium, if I have it, the medium, then I can do this simple experiment, this Snell law refraction experiment, and then I can even calculate, I can suggest what's the refractive index should be on that medium. So that is actually like identifying the medium, like you calculate the density of a copper, then you can identify that, right? Any object density by measuring the volume and mass also. And the similar, there are tables with the refractive index. Then if I measure the refractive index, I can really identify. That's another aspect we can do in the real class setting. So we have various type of classes. So we'll do the similar one here. If you go to the simulator, it says in the second medium, you can pick mystery medium 1 and then mystery medium 2. You can do exactly the same experiment we just did. There's no difference. There's nothing new. Exactly same experiment. Collect a data set, incident angle versus refracted angle. Calculate the n, and then you make a graph, then check the value with the graph also, okay? Then by knowing that number, we can get an idea what that material is technically, okay? All right, so let's go into table number 6. Any question, problems, any concern? Okay, so you collect that and then you complete this table. Okay, I'm not gonna go every single part of that, but you can definitely do it. I will complete as quickly as possible. I'm gonna do first mystery material 1. Okay, I'm getting like about 2.1 to like 2.4 range. So which mean about like 2 point maybe 25, probably the average value. So that's very large. Really, technically that represent something like diamond, okay, in terms of material. That's medium A, mystery A, and then I'm going to do mystery medium B. So mystery medium B is something close to maybe water towards some sort of glass. It's about 1.4 roughly, or 1.39 maybe. That's what I got, okay? So please complete that. Then we can take a look at the graph on that in a bit. Any question, guys? Okay, then let's continue into the table number 7, which is about the same kind of table we earlier created for sine values of the measured angles. Equals sine in radians from table number 6. Equals sine radians table 6, and then I can click and drag. Make sure you increase the number of decimals into 2 or maybe 3, because I can leave at least 3 or 4 significant figures. Okay. Okay, then we'll make a graph. Any question? So you have to record the information too. Okay, incident medium is air, and the other medium is mystery medium. So make sure you record that. Don't record the n at all, because n we don't know. That's the one we try to find. Okay. So you need to record that too here. Incident, I'm gonna put equal air, and then the refracted, we can say mystery medium A. Okay. Same incident for the other one, but the refracted medium is actually medium B. Okay. We don't know what ACN is. We can find it by using the slope of the graph. That's the plan. Any question? Okay, then let's continue into next part. We'll make a graph. So similarly, like we done earlier, insert pictures, chart, scatter plot itself, and then we'll make the graph, both graph inside the same chart area. Select data, add X values for, I'm going to put here series name as mystery A, X values sign refracted for case A, Y values sign incident for case A. Click OK, add series 2, we can say mystery B, X values refracted for mystery B, Y values incident for mystery B, click OK again, and then do the formatting for the graphs. Axis title, chart title, and then the trend line. I have two trend lines. You have to do both trend line for this case, mystery A and mystery B. And I need the both trend lines equations visible. All of those I think everybody know, but if you have any difficulty, always ask, okay? So by now we did this kind of graphing, things like that many times over last few experiments. Hopefully everybody much familiar now. Chart title, I'm going to give you a title look like what, maybe this is again same kind of title. Sine theta incident Y versus sine theta RE, which represent refracted, x-axis title sine theta refracted, y-axis title sine theta incident, there's no unit. Okay, then figure number 4 you can rename as sine theta incident versus sine theta refracted. And then we'll work on table number 8. Any question, guys? Okay, then that seems to be fine. Always ask if you have any questions. Okay, then let's do the same analysis we done earlier. Since we have a calculated values, we can take a look at calculated average. Yeah, that should be mystery A, other one should be mystery B. Yeah, very good. So I will edit that. Please check that. Okay, table number 7, I mistakenly wrote left-hand side 2 column as B, that should be A, right-hand side 2 column should be actually the B. Okay, yeah, that's exactly correct. Yeah, please check that. I think this one I did select correctly. Let me check that again. Yeah, blue one is the first one. That's fine. The graph is fine. Let's do the table number 8. Mystery A. We can check the average from the table number 7. Calculated average, actually we did not. We have calculated average here, table number, I think I have mistakenly deleted the table name here. Please check that too. This table, after table number 5, this one should be table 6. Due to some reason it's not there. If the name is not there, please add that name. Okay, probably I deleted mistakenly earlier, or I may not written that at all. Check that also. Table number 6, which actually showing us the analysis of law of refraction for the mystery material, or you can say analysis of law of refraction for mystery mediums. Okay, medium A and B. Make sure the name must be there. Okay. All right, so let's go back to here. Equal average. And I can take the average from table 6 for mystery medium A. It's a little bit higher value, 2.3 or so, equal average mystery medium B, table number 6. A bit lower value, I can keep maybe like 3 decimals or 4 because it's a calculated number. And you may need these functions also. Okay, right here I need only one function under the table number 6 to calculate the n. Because both functions are similar, at least put one function there. And for the table number 7, I need at least 2 functions to show how I did the sine theta. I can put it on top of the table, sine theta in, and then another function to show how I did the sine theta re, at least 2 of them. Because I'm reusing the same function, I don't need to add the same function again and again. But you need to add those 2. I add just above the table 7. Okay. Then under the table number 8, I can add the average, at least one of them here. This is in, we can say, cal AVG. And then we can find the numbers from the graph as we done earlier, right? So blue one is for mystery A. You can add actually the, I forgot earlier to mention here, you can add the information about those data points by using the legends, right? If you add the legends, get rid of the dotted line. We don't need the linear fitting to tell us what the linear fitting is. We know that, but we would like to see what these data are because there's 2 data set in our table. So it is better to see what these data are. Okay, I'm going to leave it on the very top. Then I know exactly what is what. Okay, so somewhere right here you can leave it. Then by looking into that, we know blue is water. This one is glass. You can do the same thing here. For this one also, we can add the legend. And I'm going to get rid of the linear fitting we don't need. But we can keep the other 2. That's information important because I need to know which one is which. Okay. Okay, now you can see blue one is mystery A, orange one is mystery B. Okay. Mystery A 2.3346 and mystery B 1.4025. Then you can compare them. Okay. We're doing PD, not PE again. We're comparing those 2 now. For these 2, we definitely don't know what is what. We're just comparing the 2 methods. Any question, guys? Okay. PD, difference on the numerator, average on the denominator. Okay, make sure you have a small number of sig figs, which mean basically only two significant figures at any given time. When you calculated any errors, do not show more than two sig figs, okay? So those two numbers show anyway good because it looked like those two are closely matching because our calculated values. But if I know the real numbers, I can compare to those like we done for previous case, okay? I'm going to add one quick information here in for mystery material A from graph is equal to slope of the graph. Okay, so that we need to add. We don't do any calculation, but that need to tell how we actually get that number from the graph. Okay, guys, any question? Okay, then let's move into the last part. In last part, what we're going to do, we're going to investigate the total internal reflection. Remember earlier we talk about that. If I want to investigate the total internal reflection, I need to send the light from the higher refractive index to the lower refractive index. So you need to change the upper part of the simulator white color part into a glass, and then lower part I'm gonna change into water. Now you can see light ray coming from the glass. And then if I have a smaller incident angle, I'm going to start like maybe 10-degree incident angle. You can see clearly it is going through the glass. But if I increase the angle slowly, incident angle, you can see the refracted ray coming towards the boundary. And then that refracted ray at some point will disappear and then completely reappear on the other side. Okay. So now anything beyond that point, you can see the light rays are only in the same side. So that because of total internal reflection happening now. Okay. All right, so that we can investigate again for all four mediums to identify what is that critical angle is. By using the critical angle, we can identify what is the refractive index is. By identifying the refractive index, maybe we can identify even the medium if we want to. So let's do that part on table number 9. So I'm going to start from the water to air. Incident should be water, upper part should be blue, lower part should be white. Okay. Water to air. Then I have to slowly increase the incident angle until I see disappearance of the ray in the white color side. Okay, it should completely disappear. As soon as it completely disappears, then you read the incident angle. Incident angle right now is about 30, 40, almost close to 50, or maybe you can read into 51. I'm going to read into 50.5. Okay. All right. By using that, we should be able to calculate the critical angle. If you remember the formula which I did earlier, so when the total internal reflection happen in 1, sine theta 1 is equal in 2 sine theta 2. In 1 is actually where the incident medium is. I wanted to find that in. Angle is critical now. In 2 is the air. In 2 is 1. And then sine angle for that side is 90 degree. So this is equal 1. Basically, n we can calculate by doing 1 over sine theta of c. So that's a very useful way to get the total internal reflection. Okay. And also using the total internal reflection idea to get the refractive index of the medium. So let's check it out that here. 1 divided by sine open brackets, radians I did always for any trig functions. The angle is C 150, close bracket twice, hit enter. So I'm getting about like 1.295. So that is roughly about 1.3. It's fairly very close. Okay. So don't keep too many sig figs. Maybe like one extra is okay. All right, guys. Any question? N from critical angle, 1 over sine of critical angle. Then we can compare to the known. So the known value of water one, we know 1.33, we'll compare that, okay? So in this case, actually we calculating PD, okay? So you can say PE, not PD, PE because we're going to compare to the known value, equal sign, parentheses ABS open bracket, expected value for water 1.33 minus calculated value from critical, close bracket, divide by 1.33, close bracket, multiply by 100, about 2.5% error. Any errors is just our measuring errors because when I measure the angle with the protractor, otherwise it should be much lower than even this, okay? So that also the function for this table we can include here. Okay, guys, question. Okay, we can check that for other mediums like we did water. Let's do glass then. It's the same concept. You start from the very low angle, vertically closer to the vertical line, and then slowly increase the incident angle until you see disappearance of the refracted ray. Whenever it disappears, you read the incident angle. Okay? Now it's about like 30, 40, 42, 42.5, or close to 43. Then these you can just click and drag. But when you do the PE, you have to be careful. You can click and drag. However, you have to re-edit the expected value. Okay. Expected value is not always 1.33. Case by case, it's changing. So you can click and drag, but you have to go up again, edit the expected value for the glass, expected value 1.5. If not, you will see it look like very large percentage error. Okay. If you see it, make sure you edit that carefully. So this should be 1.5, and then this also should be 1.5. So now again about 2%. Make sure you do that editing. Otherwise, when you click and drag column E on last table, you will be getting maybe large percentage error because expected value changing by case to case. Any question, guys? Okay, then let's do the other two, mystery A and then mystery B. Mystery A. We can start from very low and then slowly decreasing back until the rays disappears. When it disappears, we'll read the angle. Okay. So for that, incident angle is about like 20, 25, maybe 24. And for that expected value, we'll get from the previous table, calculated average or the graph value. Either is fine because both of them are very simple, very similar. I'm going to take the mystery A graph value, 2.3346. Then I compare that to the expected, the value I got here, okay. 2.3346, and then right here, 2.3346. It's about like 5% error. So you can check again the incident angle when that light rays disappear. That's critical angle. When you're measuring that, that accuracy is so important. Okay. Then you do mystery bit. Any question, guys? Mystery B, the graph value I got earlier, 1.4025. Let's compare that. Okay. 1.4025. That error is very little bit larger. I'm going to take a look again why. Maybe my critical angle is wrong. Let's check again. That can't be such big error. Maybe about 2%, 5% is fine. 30, 40, oh, this is wrong number I used earlier. 30, 40, 45, about like 46.5. That's one. Yep. Okay, now it's got about like 1.7%. Check those numbers, okay? Particularly the PE is actually difference for each case. I'm going to add the PE for each one of these because it's a very different PE for water. And then I'm going to add PE for glass. And because the expected value is different for each case, otherwise we don't know. It's not directly dragging down that column, okay? So be carefully check that. And PE for mystery B. Okay, guys, any question? Okay, so I think it's good. We can briefly take a look, little bit of more idea into the plane mirror image formation. That's what we're going to start on next week in our lesson. So we'll briefly take a look that idea. Okay. Any question, guys? Any problem? Okay, then let's take a look the plane mirror image formation a little bit. Then we can start from there next Monday, since we have a few more minutes. Let me open up something to write up this. And you need a lab report for this one, okay? That's the individual lab report. Before you're doing any other lab report, make sure you read all the comments which I wrote for your first lab report submission. That is, I think, experiment number 2. Read that, okay? Then you can get a better idea if anything went wrong, what's the problem, and then so on. That will give you a better idea about to correct out any of those problems. Okay, guys, so let's, because we talk about reflection, but we did not talk about any image formation. That actually the main concept of, main part of this next chapter, okay? Geometric optics chapter. So we will take a look at least image formation of the plane mirrors right now. Then we can go from there to the curved mirrors and the combination of, and the lenses and the combination of lenses and the end of that chapter. Okay. Okay, guys, any question? Okay, seems to be no question. All right, let's see the image formation from the plane mirror. Let me share this. Okay, now the reflection we already discussed, right? Reflection mean if I have anything coming in, and then if that hit the boundary, and then if boundary doesn't allow light to pass through, then that should be come back to the same side, right? So that is the idea of uh, reflection. So which means if I have a light ray, if I have a light ray which comes in and then hit the boundary right here, if that light ray does not allow to pass through here, and then if that surface is very shine, very polished surface, then only you can see the reflection. Otherwise, if that surface is like in microscopic level, not shine and polish, what will happen? There is still reflection, but that reflection is scattering out everywhere. So the rays are going everywhere. When you observe from this side, you will not see any image. That's the problem. Okay. Now, if it is a very shine surface, then this exactly 90-degree line, which is the normal line, will create theta I and then theta R. The screen is shared. I can see that on my other window. You have to take a look again why it's not showing up. Is anybody have any problem with the screen? Okay, so take a look again. I can see from my other window it's shared. Okay. All right, so we know the law of reflection, theta I should be equal to theta R. We can use that principle to identify how the plane mirror image actually formed, okay? So let's take a look at that. So how the plane mirror image actually formed, let's consider I have a mirror here, and then let's consider I have an object, this is ground, okay? And this is the mirror right here. I'm going to put M for mirror. And then let's put an object right here. Now this object will generate an image somewhere here. We know that should be on the other side somewhere here. We can see that in generally. Usually the mirrors producing, the plane mirror producing exactly similar size uh, object, similar size image on the other side in similar length in terms of measuring the mirror exactly right here. This separation we call the distance to the image. Usually we put di. And in this separation from the lens to the object, we call the distance O, which means the object, okay? I is the image, O means the object. Now let's see how this actually can be identified by using the concept of law of reflection. So let's do two rays, for example. Let's consider one ray directly hitting here, which is the ray coming starting from the very top right here, very top of the object, and then it directly hits 90-degree angle to the mirror surface. Then what it does, it should obey the law of reflection. It should reflect it back itself because incident and the reflection angle should be the same. So if it is 90-degree hit, it will reflect it back as it is, right? 90-degree. So that means that ray, reflected ray, is on top of the incident ray. So if you expand that ray to the other side, that expanded, that extrapolated ray, this dotted line blue is the extrapolated. Those are not real, okay? Nothing real there, only an illusion happening inside our eye. Really nothing there, we know that, right? Behind the mirror, nothing there, right? That's a fundamental difference between the monkeys and between the some animals and the human, right? When the dog or some other animal see his image through the mirror, then the animal can't really identify that whether that's real or not. If a bird see that, bird is actually trying to go through by thinking another animal there, because he don't know even that is him, his, or that it image or anything, right? That's a very fundamental difference between the animals and the human. Only the human has a brain power to really identify that. So this is not real, so I don't need to worry about it. Okay. All right. So this ray right here, what I'm drawing in the dotted line, is actually called the virtual. Virtual means it's not there, but we're drawing to identify this image. So anything we do a dotted line in our ray diagrams later is actually virtual rays. Okay. So now these are real optical rays. The dotted ones are the virtual rays. So I need to identify the exact image, I need to identify at least one point of the object. Let's try to identify this exact point, this tip right here. If I identify that tip on the other side, then I can do the same for every other point of the object. So that will make the image, complete image. Okay. To identify that, one particular point, you need at least two rays or more. That's a fundamental concept. So we'll do another ray coming from here, maybe hitting somewhere like that. Then that ray hits here, then we know that should reflect at this exact moment with the same angle as it incident. So which means that will reflected from there right here, exactly same angle as it incident. If you extrapolate it backward, it will pass through exactly this point right here. That point can generate the very top point of the object. If I do the same process again and again and again for any other point right here, doing the two rays, I can actually build the object, build the image, okay? So which means that finally we will get the image right here. Technically nothing there. That's a virtual image. Virtual image means the image is formed by using the virtual optical rays. There's no any real optical rays behind the mirror. So we call this image is also a virtual image. Okay. Virtual image means nothing really there. That's the idea. Okay. So that is virtual image. And if you look at the geometry, geometrically, I can say height of the object, which should be equal to the height of the image by just using the geometry. For the plane mirrors, height of the object is equal to the height of the image. And if you take a look, the object which is upright, upright means it's in the upward direction of the positive y-axis. And then if you look at the image also very similar to that, right? So image also upright. So then I can identify, for example, the magnification. Magnification means how larger or how smaller the image relative to the object. If I do that, magnification, I can write image height divided by the object height. Relative to object height, how larger or how smaller the image is. So plane mirrors, we will get usually magnification as 1 because there's no any real magnification in the plane mirrors at all, right? So we can clearly see that should be equal to 1. Now, when we're talking about the magnification, that is geometrically again, okay, we don't need to do anything. We're going to take a look at our ray diagram. Okay, now this diagram is actually called the ray diagram. Ray diagram. If I look at the ray diagram, that is our geometric diagram. That's why the whole chapter is called the geometric optics. If I look that, I can just basically understand everything what's going on. And this magnification, usually we write M. This we can write by using either height of the object and the image or distance of the object and the image, because geometrically, if you look this triangle, for example, if I draw a small triangle here, then this triangle, I can use maybe this angle theta. This angle should be also theta. Because of that, if I use, for example, sine theta for this one, sine theta should be h0 over d0, sine theta for the other one, hi over di. So sine theta is equal, which means hi over h0 should be equal to di over d0. That's again from the geometry. However, when we're doing these distances, unlike the heights, there is a one specific condition we're going to apply. That is a basic definition we need later when you're doing the mirror and the lens equation. If I'm measuring anything, that's important, okay, how we define this. If I measure anything, if I measure any distances from the mirror or lens later towards the real optical lines, which mean, for example, D0 is actually real. Everything on that side is real. Anything measured to the real optical lines are we considered as a positive numbers, okay? Anything we are measuring towards the virtual optical lines are considered as a negative numbers. This is nothing to do with x-axis positive or negative. Do not think like that. So there's no x or y here. Okay, later when we do the ray diagram, do not do that because sometime later in the mirrors and lenses, the virtual lines gonna appear same side as the object is. Then you have to be very careful how you do the measurement. How we do the measurement from mirror or lenses to the object or image. Now everything towards the object are associated with the real optical rays, positive. Everything towards the image associated with the virtual, for this case only, those are actually negative. Because of that, to represent that, I have to put the negative sign here. So this is actually a negative number. This is also we're going to put negative sign here. That negative sign represent upright. Okay. So that two definitions we need here. One is the measurement. Other one is the anything is upright, which is actually a negative itself. That negative sign means something, okay? So we will talk about that later when we go into detail into the chapter work next Monday. So we will take a look very in detail application of lenses equation and the mirrors equation, okay? So everything based on just simple this ray diagram. That's the one you have to focus as we continue next week. All right, guys. So we can stop here. If you have any question, always, as always, stay on the call or reach out, okay? Otherwise, I will see you guys then next week.